So, hello all, can you hear me?
Yes, we can.
Let's start in 2 minutes. All right, let us begin. We're going to continue our sequence of lectures on recurrent networks. Specifically, we're going to be talking for the next couple of lectures on sequence-to-sequence models. And the particular form of model that we will be talking about is connectionist temporal classification. So what is sequence-to-sequence modeling? It's one where an input sequence goes in, some x1 through xn, and a different sequence y1 through ym comes out. For example, in speech recognition, speech goes in, a word sequence comes out. Or in machine translation, one word sequence goes in, a different word sequence in a different language comes out. Or dialogue systems, where the user response goes in and the system response comes out. So in all of these, the length of the input sequence need not be the length of the output sequence. In fact, there need not even be any notion of synchrony between the sequence of inputs that goes in and the sequence of values that come out. So we've seen one example of this, speech recognition. Here, a speech signal goes in and the text comes out. Now, this has a very specific ordering relationship between the input and the output. Here, the output is order synchronous with the input, but not time synchronous. Do you guys remember what I mean by that? Order synchronous, but not time synchronous. Do you remember this? Right. So for every section of the input, there's a corresponding symbol in the output. If you permute the input, the output will get permuted in the same order. In other cases, like in machine translation, there may be no notion of such synchrony. If you're trying to translate English to German, I ate an apple goes in, ich habe einen Apfel gegessen comes out. And observe that, I over here becomes ich, but ate becomes habe and gegessen. There's really no one-to-one correspondence between the input and the output. The specific form of sequence-to-sequence model that we've already seen in the last class is this one, where there's order synchrony between the input and the output. And that's what we'll close out the lecture on today. So here, the input and output sequences happen in the same order. So the output is order asynchronous in that the portion of the input that corresponds to this output is the portion immediately preceding it. So the portion of the input that corresponds to this output would be this portion of the input and so on. There's synchrony, but not time synchrony. So here, the questions were how do we perform inference on such a model? That is how to output times in asynchronous sequences, and then how do we train such models? And the problem of inference is something that we partially addressed. We will come back to it at the end of this lecture. The more important problem is how do we train such models? And we started with this notion that if the training data included the input and the output sequence along with the alignment of the output sequence. Does anybody remember what we meant by the alignment over here? Anyone? Do you remember what we meant by the alignment? Someone? A yes, no would do. The time sync. So the alignment basically tells you which input time corresponds to each output time, the correspondence between the input and the output. If that were given, you'd be informed where each of these output symbols were generated. And you, of course, you can replicate them and the gaps before them, and then you can compute a divergence between these two sequences. And the way we define it now, the divergence between the target sequence and the actual output sequence is going to be the sum of the local cross entropies or KL divergences, which simply becomes the negation of the sum over time of the log likelihood of the log probability of the target symbol at each time. Now, this is something, keyword, just observe this. We're going to use this again and again, okay? Now, this comes out because we know that the cross entropy loss is simply the negative of the log probability of the target symbol. So we are summing T cross entropy losses. Now, if I take the derivative of this divergence with respect to each of the outputs, then what I'm really doing is taking the derivative of the sum of several KL divergences. But then the overall divergence, if you look at the what component of the overall divergence depends on any specific YT, that's simply going to be the local divergence at that point. And so, although the divergence itself is the sum over time of all of these KL divergences, the derivative of the overall divergence with respect to any specific YT is simply going to be the derivative of the local cross entropy with respect to that YT, which is simply going to be the derivative of minus log of the probability assigned to the target symbol with respect to the probabilities assigned to all symbols by the network. And since this loss only factors the target symbol, the derivative of this loss with respect to the other symbols in the vocabulary is zero. And the derivative has only one non-zero component corresponding to the target symbol. And that's simply minus 1 over the probability assigned to the target symbol. Again, this is nothing new. We saw this a few lectures ago. So is this making sense, everybody? Is this clear? We're going to use it. Okay, easy. The problem was, how do we deal with it when there is no alignment provided for the training data? So you're given the output sequence, like Beefy, but no timing information. What do we do? So we saw one example where we could try to guess the alignment and do so iteratively. So you initialize the alignment somehow. You train a model with the initial alignment, and then using this trained model, you go back and realign the training data using Viterbi alignment. And then you can use the new alignments to go back and retrain your model and iterate this process. This is what we saw in the last class. We said this would work, but there was a problem with it. And what was that problem? Anyone remember? What was the problem with this? Anybody? So it's highly dependent on the initialization. But anyway, first let me release the first poll. Can you guys see the poll? Okay. 10 seconds. All right. So here's what everybody thought. And let me ask you again, right? Is this first statement true or false? Viterbi training explicitly estimates the alignment of each training instance and computes the divergence. True. It requires re-estimation of alignments in every iteration. True or false? The second one, also true, right? Because when you update the model, then you might get a better alignment. The problem here is heavily dependent on the initial alignment. And so it's prone to look poor local optimum. So how do we get around it? Here's an alternate solution. We do not commit to an alignment during any pass. And so what does this mean? We're going to be training without alignment. We know how to train if the alignment is provided. The problem is that the alignment is not provided. One solution was to guess the alignment. The second solution is to say, I'm going to consider every of the symbol sequence to the input. What do we mean by this? Now, remember again, when we wanted to align the symbol sequence to the input, the first thing we did was to grab the rows of the probability table generated by the network from the input and create this reduced table. Do you remember this table, guys? Right. And so this table, any path through this table, which started from the top left corner and ended at the bottom right corner, and always either proceeded horizontally or diagonally one step down, was guaranteed to be an alignment of the symbol sequence to the input. And then we could compute, we were computing the most likely alignment, and then we were computing the divergence with respect to this most likely alignment. And this divergence was simply the sum over time of the negative of the log likelihood, log probability assigned to the symbols on the most likely alignment in the current iteration, right? This was what we had. But then the most likely alignment is just only one of many possible alignment input to the symbol sequence. And the set of all possible alignments we saw could be represented using this graph. Do you guys remember this graph? It's also called a trellis. Do you remember this graph, right? Yes. And so what we've really got is that each alignment that you can obtain from this graph has a probability. All we did was to pick the alignment that was most probable, but every other alignment also had a probability, right? So in other words, if you consider all possible alignments that you can derive from this graph, they have a probability distribution. And the most probable alignment is the one alignment that has the highest probability in this distribution. Did that make sense? Right. So instead of just picking the most likely alignment, why don't we use a statistical expectation over all possible alignments? So in other words, I'm going to compute the divergence with respect to every single alignment. And the divergence with respect to any alignment is simply minus sum over t, the log of the probabilities assigned to the symbols on the aligned path, right? So I'm going to compute the divergence with respect to every single alignment, but then I'm going to multiply this divergence by the probability of that sequence, of that alignment, and then sum over all possible alignments. So this is using the entire distribution of alignments. The more probable alignments will get more weight, the less probable alignments will get less weights. That makes sense? Yes, no? Can you see some issue with this? The computational cost, right? So before we get to the computational cost, let's have our second poll. Okay, 10 seconds. That's right, Theodore. Okay, 5 seconds, guys. Okay, let me end this poll. And here's what you guys thought. Let's verify, right? The first statement, the training without alignment computes the average divergence over all possible alignments, true or false? True, right? You're taking the expectation. It requires explicit estimation of the alignment, true or false? It doesn't, right? You're training without alignment, literally. So you should not be requiring the estimation of the alignment. So true and false. So how does this work? We want to take the expectation over all of the divergence over all possible alignments. But for any given alignment, the divergence is simply the negative of the sum over t of the log of the probability assigned to the symbol assigned to time t by that alignment. So is this term, which is the divergence for any alignment, making sense? And is this larger expectation making sense to you guys? Yes or no? Right? So, okay. But then the expectation operator is linear. Okay, so Christine, what we are really doing is taking the expected divergence over all possible alignments. Correct? Christine? And the divergence for any given alignment is simply minus of the sum over time of the log of the probabilities assigned to the symbols on that particular alignment. That makes sense? And so this is what we are taking the expectation of. But then this is the expectation of a sum from the linearity of expectations. That's the same as the sum of the expectations. Is this making sense? Over here, the second term. And so the divergence is minus of the sum over all time of the expectation of the log probabilities assigned to all the symbols, at all possible symbols at time t. So what does this mean, right? You still get the minus of sum over time t, but then this inner term, you're going to sum over all the symbols. And what will you sum over all the symbols? The log of the probability assigned at this node, which is this guy over here, multiplied by the probability of the node itself. But what is this probability? This is just the standard formula for expectation. The expectation is the variable that you're taking the expectation of, multiplied by its probability, right? So this is the log of the probability assigned to the tth symbol in the sequence. And this is the probability that the tth symbol in the sequence is that particular symbol. Now there's a given capital S and X, which is to say they're working off this graph. We are given the input and we are given the compressed sequence. So what is this guy here? This is the probability of aligning a specific symbol S at time t. So this overall summation is the probability of, say, if we consider any given time, say this time, right? This guy is the log of y4b. And this term is the probability that a randomly chosen alignment is going to go through this node. So what we are doing is summing over all these rows. Here, the negative log of this term multiplied by the probability that a randomly chosen alignment goes through this node, plus the negative log of this term multiplied by the probability that a randomly chosen alignment goes through this node, and so on, sum down the column. That's what this inner sum is. And the outer sum is summed over the entire sequence. So Mariam, I will answer that question shortly, but is this making sense? The rest of you, is this making sense? Right. Any questions? Okay, so we're going to work off this, right? So what is this guy? Now the focus becomes this term. This is the probability that a randomly chosen alignment goes through a specific node at time t. That is nothing else. So what is the probability that a randomly chosen alignment goes through this node? That's going to be the total probability of the entire subgraph that goes through this node. Is this making sense? Right. Now, I want you to remember something. If you look at this overall graph, what is the total probability of this overall graph itself? What is the total probability of this overall graph? No, it is the total probability of all paths, all alignments of the symbol sequence, correct? So the total probability of this graph is basically every way of aligning this symbol sequence to the input, which is simply going to be the probability of this symbol sequence across all possible alignments. Does that make sense? If you multiply all of these and sum them up, there's no constraint that they will sum to 1. So this is one way of generating B phi. This is another way of generating B phi. So this encapsulates every possible way of generating B phi. If I sum all their probabilities, I'm just going to get the probability of generating B phi. That makes sense? What about the rest of you guys? That makes sense. Okay, so when I do this, the total probability of the subgraph that goes through this node is the probability of generating B phi such that the third input aligns to E. Did that make sense? The probability of the subgraph. That's what we mean. So the probability of the subgraph is the probability of the entire input sequence and having the specific state at time t correspond to the rth symbol in the sequence. Okay. So this is what we want, right? And so this is the term we must compute. Are you guys with me? Over here. The rest of you, okay. So can you give me a few thumbs up? Because for each node, the probability was generated by the node, by the network. Remember, this entire going back way back when, this was generated by the network. We just copied these probabilities over. Remember that, Mariam? Right. So we have all of the things. So the question is, how do I compute the probability of this subgraph? Basically, how do I compute the probability of the subgraph encapsulated in pink? That is the total probability of aligning the third input to this to E and generating B phi. Now I can decompose that into two parts. This subgraph has two parts. The first part is this portion leading from the source to this node. The second part is this portion, which comprises all paths going out of this node to the end. So I can say the total probability of this entire graph, subgraph, is the probability of this portion that's encircled in blue times the probability of the portion encircled in red, given that the initial portion of the input lay in the subgraph, aligned to the within the subgraph. Did this make sense? Right. So the probability of the blue graph times the probability of the red subgraph, given that the early alignment lay within the blue graph. The rest of you, did that make sense? Because, okay. So give me some thumbs ups, guys. I'd like to see 25 of them. And so then here's the thing. What is the condition X? This is the input. All of these probability, everything is conditioned on the input audio. That answer each all? Right. So, Chol, did that answer you? Well, I'll just continue. I assume so. Okay. because everything, and so here's what we were given this input. We computed this probability. So these probabilities are conditioned on the input, which is why everything is conditioned on the input. But then here's something you observe. These probability vectors are just drawn off this recurrent state, which means that the probability vector over here that was computed of this hidden state and did not directly influence this probability vector. This probability vector is only dependent on this hidden state. And the hidden state, of course, is dependent on the input sequence. So these vectors have no direct dependence on each other. They are only related to each other through this input. Did that make sense? Right. So to explain this better, if I were to randomly sample some symbol from this distribution, that is going to have no influence at all on the probability vector that I will compute here. So anything I do with this vector will not influence this guy. These two are independent, given the input. They are conditionally independent. That makes sense? Okay. So what this means is that when I go to this guy, if I look at this one, the probabilities that I get in this portion of the graph have no relationship to the probabilities that I get in this portion of the graph, because these two are conditionally independent, which means that the probability of lying within this entire subgraph can be simply broken into two components. The probability that the initial portion of the input falls within the pink subgraph, and that the latter portion of the input falls within the second subgraph. So the probability of this entire subgraph is going to be the probability of this pink subgraph times the probability of this blue subgraph with no conditioning. Did this make sense? What about the rest of you? This makes sense. Okay. I'm going to call this first portion the forward probability. I'll call it alpha TR. Alpha TR is the probability of the subgraph that ends in the rth row at time t. I'm going to call this beta TR. Beta TR is the probability of the subgraph that starts from the rth row at time t. So are these symbols making sense? Do you understand what these symbols are? Okay. So let's see how we can compute this guy. We don't pass through x. What do you mean we pass through x? X is the input given. What is the probability of all paths in this portion of the subgraph? Is it 1, Mehul? They're passing through the node, but after that, there are many possibilities, right? And are all of these going to, this is just a portion of a graph. Remember, the entire graph is the probability of B phi, correct? Which means that any subgraph is going to be less than the probability of B phi, correct? Yes or no, Mehul? So will that be 1 then? Right, okay. So let's see how we can compute this guy, the alpha TR. This term is simply the total probability of all paths that end up at the rth symbol at time t. So alpha 3e, for example, is the total probability of all paths that end up against the first e at time 3. That makes sense? Over here? Okay. And then how can I decompose this? Look at this. There are only two ways to come to this guy. So if you're going to end up in this node at time 3, there are two ways to do it. You can end up in either B at time 2 and transition to E at time 3, or somehow end up at E at time 2 and transition to E at time 3. These are the only two ways to get to this node, right? So is this making sense over here? So the probability of this entire subgraph is going to be the probability of the subgraph that ends up at this node and extending that by y3e, simply by multiplying y3e plus the probability of the subgraph that ends up at this node, the second node, extending it by y3e. So is this one making sense? Yeah, alpha 3e over here. And can someone tell me what is this guy here? The probability of the subgraph that ends up at 2b. What is that? That's alpha 2b, right? And what is the probability of the subgraph that ends up at 2e? What is this? The probability of this subgraph. Using the same logic, guys. Alpha 2e, correct? And so this is what you have. The probability of the subgraph that ends at e at time 3 is going to be, which is alpha 3e, is going to be alpha 2b times y3e plus alpha 2e times y3e. Is this making sense? This one here. Right. Or to generalize, the alpha for at any tr at any node is going to be the sum over all the parents of that node of the alphas at the parent nodes multiplied by y by the probability of the node, which is ytsr, the probability assigned to the rth symbol in the sequence at time t. So is this equation making sense? This one here. Okay, I'll pause here for 25 thumbs ups because this is kind of key. $18, $20. Okay, let's stop it. So this is how it is. The alpha at any tr, at any node tr, is the sum over all the parents of the node of the alpha of the parent times ytr. That's it. But once I have this formula, I can do something magical, right? So here's how it worked out for this particular example. Alpha tr, there are only two parents to the trth node. One is at t minus 1, r minus 1, and the other is at t minus 1, r, right? So this is t, so this is t minus 1. This is r, so this is r minus 1. The two parents are t minus 1, r minus 1, and t minus 1, r. So the alpha tr is going to be the sum of the alphas at t minus 1, r and t minus 1, r minus 1, and the sum is multiplied by the node probability, which is ytsr. Is this making sense? Over here. Okay. And so here's how we're going to do it, right? Now we define a forward algorithm. How does the algorithm work? I'm going to start computing the alphas left to right, top to bottom. Now, at the very first time, I know that the graph cannot begin in any of these nodes, right? So the probabilities of the subgraphs that end in these nodes is going to be 0. The probability of the subgraph that ends at this node is simply going to be the node probability itself. It started here and ended here. So is this initialization making sense here? This guy. Okay. And then I take a step forward. Over here, this node only has one parent. So the only parent I have to consider is alpha t minus 1, 0. And then I multiply that with, yt as 0. This is the 0th row. In this case, I just consider that I multiply the alpha here by the probability here to get the alpha over this node. But for all of the other nodes down the row, I'm going to be summing two alphas, the alpha immediately to the left and the alpha diagonally above, and multiplying that by 1. So I can use this formula to compute the alphas all the way down the row, down the column at this time. Is this making sense, how I did this? I just basically use this formula here. And using this formula, I computed the alphas down the entire column. Alpha 0, 0 is simply going to be the node probability, right? What is the probability of the subgraph that ends here? The subgraph is just the node. So it's just this one, right? And then I can use my recursion to compute the end of the subgraph. The tth node is I start here. What is the alpha for the subgraph that ends here? I compute that alpha for each of these. Then I go down here. What is the alpha for the subgraph that ends here? I'm doing this for every single node. Every single node has a subgraph that ends there. Did that answer your question, Elvis? Right, and so I can compute the alphas here. Then I can use these alphas to compute these alphas, and then I can use those to compute these alphas. I work my way all the way to the end, and I'm going to have the alpha for every node in the graph. So do you see how this happened? Is this making sense? Yeah, okay. And so here we are, right? We know how to compute, and of course, the alpha for this final node is going to be the alpha for the total graph. So the alpha for the final node is simply the probability of the sequence. Okay? Are you okay with this? Over here. Okay, and so we're good. So that means we figured out how to compute for any given node. If you just apply the alpha, run this forward algorithm, which computes all alphas. You pick a node, and I know the probability of the subgraph that ends at this node, which is alpha tr. I can just replace this first term with alpha tr. So now the term that remains is the second guy. How do I compute the probability of the subgraph that emanates from tr? Now, just for convenience sake, so this subgraph doesn't include this node, right? But for convenience, so this is we want to, beta tr is the probability of the subgraph that comes after the tr node, everything that follows. Do you understand this? What beta tr is here? Yes or no? Right, and so we don't consider this node because this node is actually part of the alpha, right? But then just to simplify things, we will temporarily include this node in the subgraph, and we can compute the beta so we can compute the beta including this node. I'm going to call that beta hat. And then once I have the probability for the subgraph that also includes this node, I can just divide it by the probability of the node itself to get the actual beta. This is just for convenience. So is this working for you guys? Do you understand this? Over here, what I've done, I just included the node, and then once I computed the probability of the subgraph, I just removed the probability of the node. Easy. Now let's see how beta tr works out. I want to see the probability of the subgraph that starts from this node and ends at the final node. But this node has two children, right? So the probability of the subgraph is the probability of going from here to this green node and being in the subgraph that starts at the green node, plus the probability of going from here to this red node, y4f, and the probability of the subgraph that starts from this red node. So is this clear? This one? Right. And what is the probability of this subgraph over here? What is this one? What is the probability of this subgraph? Anybody? That's just beta y4f, right? Does everybody agree that that would just be beta y4f? Remember, beta y3e is the subgraph that started from here. So the subgraph that starts from here is going to be beta y4f, right? So I can just write that this beta or beta hat. So the beta hat 3e is going to be the probability of y3e times the sum of the betas of all the children of this node. Is this making sense? Here? Okay. And so here we are, right? The beta hat for any node is the probability of that node times the sum of the betas for all of its children. Simple. And so Now I can use the simple recursion to compute betas going backward. At the very first, but except I start at the end. When I start at the end, I'm still doing the beta hat, which includes the node. The probability of the subgraph that starts from here and ends here is just going to be the probability of the node itself. For the rest of them, you cannot start at these nodes. These nodes are impossible. So the probability of the subgraph that starts from here and ends over here is going to be 0, because starting here is impossible. So for these nodes, the beta terms are 0. Is this initialization making sense? Over here? Okay. Now I have the betas for all of these 0, 0, 0. And the beta at this node is y8e. Then I can take a step back. And then I can compute the betas for all of these nodes. The beta is simply going to be the probability of the node times the sum of the betas for its children. I go down and compute the betas for all these nodes. And then for all these nodes from these guys and these nodes from these guys and so on, I can work my way back and compute my betas for every single node in the graph. Right? So Clemens, why is it impossible? Is it possible? The graph doesn't have any path to this node. Does it, Clemens? You're restricted to be within this portion. Otherwise, it will not be an alignment of B-phi. Correct? If you started from here, there's no path that ends at this guy. So basically, you can't start at this. You can't start here or end here. It's not part of the graph. That's why it's 0. Okay. That makes sense, Elvis and Clemens. Okay. And so we know how to compute this beta hat for all the nodes in the graph, but the beta hat includes the probability of the node itself. So you want to divide by the actual probability of the node to get the real beta. And so therefore, the actual recursion looks like this. You're going to use this little recursion we just saw to compute the beta hat, which includes the node probability. And the actual beta is obtained by dividing the beta hat by the node probability. So is this sounding okay to you guys? Yeah. And so we know how to compute the probability of the blue graph, which is simply the backward probability. We call it backward because we computed backward, going backwards. This is beta TR. And so the probability of the graph, subgraph, that goes through the node at TR is simply the product of alpha TR and beta TR. This making sense? Okay. So now this is the probability of the subgraph. But what is the problem? What is this term? This is the probability of generating B-phi and aligning the third input to E. But if I want to take expectations, then I want a probability distribution that sums to 1. If I'm given that the input is the symbol sequence is B-phi, then there are only 4 possibilities over here for the alignment at time 3. So the probabilities of these 4 nodes must sum to 1. So how do I make it sum to 1? I take the product alpha beta for each of these nodes and divide it by the sum of the alpha betas. And that's going to give me the posterior probability of the node given the input sequence and the symbol sequence. Because I'm dividing by the probability of the symbol sequence itself. Right? So, no, it doesn't, Shrey, because look, we actually computed beta hat. And then we divided by y, and it got rid of y3. That answer you, Shrey? Right, okay. And so this, we can compute this normalization. I'm going to call this gamma. And so gamma TR is simply the product of alpha and beta divided by the sum of the products of alpha and beta down the column. And this is the posterior probability of this node given the input and the symbol sequence. And once you have the posterior probability, okay, so if I'm taking an expectation across the column, Marian, then the probabilities of these 4 nodes must sum to 1, correct? But they won't, because the product of alpha and beta is going to be the joint probability. Yeah, okay, that's it. So you normalize. And so this is the actual divergence that we got. It's the sum over the negative of the sum over all time. And at each time, it's the sum over the entire column of the product of gamma TR at each node and the log probability at that node. This is the divergence that we finally got. And this divergence is the expected divergence over all possible alignments. And that is what we're going to minimize. And so let me give you the third pole. Can you see the third pole? Okay, 10 seconds, guys. I've been too slow. All right, let me end this poll. Here's what you thought. And first statement, true or false? The second is also true, right? Both are true. Perfect. And so here's what we got. We got this aligned table, this table. We computed the divergence from this. But from this divergence, what we really want to compute is the derivative of the divergence with respect to the output of the network at each time. That's what we are going to backpropagate, correct? This divergence, from this divergence, we want to compute the derivatives for all of these guys, right? Yes. So which means that we're going to have to compute the vector of the derivatives of the divergence with respect to each of these probabilities at any time to get the derivative of the divergence with respect to the output of the network at that time. What are these probabilities? Now, if any symbol doesn't occur in this table, which means if any symbol is not part of the symbol sequence, then clearly that symbol doesn't affect the divergence and the corresponding derivative term is going to be 0. If any symbol occurs for the rest of them, you want to compute the derivative. So again, if I want the derivative at any particular time, then I can ignore the other times and I just need to compute the derivative of this inner summation at that time with respect to all the probabilities for all the symbols in the vocabulary. And clearly, if any symbol doesn't occur in this column, then that derivative is going to be 0. For the rest of it, what does it look like, right? These terms are what we must compute from this one here. And this is the derivative of the divergence with respect to, so if I take a look at any given term, say this probability, then I want to compute the derivative of the divergence with respect to that probability, which is the negation of the sum over the column of the derivative of the contribution of each cell in that column to the divergence, which is gamma times log y, right? So the derivative of the divergence with respect to any symbol is the sum over the column of the derivative of the gamma, product of gamma and the log probability with respect to this term. So is this making sense here? Just the math. Over here. If it doesn't, no matter, just trust me. This is the term that we are now left to compute. What is the derivative of the product of gamma? Again, at any given time, the divergence is simply the sum over the column of minus of gamma times log probability, right? So you want to compute the derivatives for each of these cells and sum them up. So if any symbol doesn't occur, for example, this symbol t doesn't occur here. So the derivative of the divergence with respect to the probability of t is going to be 0. B occurs, wait a minute. I'm losing something here, right? So B occurs once. So I'm going to get the derivative of this guy, the gamma for this node times the log y for B. The derivative of that with respect to YB is going to be the term corresponding to B over here. E occurs twice. And so the term for E is going to be the sum of the derivative of gamma for E over here times log y for E plus again the derivative from this contribution. So for E, we would be summing two terms. For B, there's only one term. For F, there's only one term. For the rest of them, the derivative will be 0. Okay. And we are left with, what is this guy here? What is the derivative of gamma times log with respect to y? And of course, if you just use your standard derivative rules, the derivative of gamma times log y with respect to y is going to be gamma over y. If I take the first derivative, this term times the derivative of this term, which is gamma over y, plus this term times the derivative of this term, which is the derivative of gamma times log y. So is this equation making sense? The second one. Okay. This is easy. We've already computed gamma. We know what y is. This term, this gamma term was computed through a horrible forward-backward equation. Computing this derivative is devilishly hard. When something becomes too difficult to compute, what do you do as an engineer? What would you do if it's very hard to compute it? Just set it to 0, right? You don't even bother estimating it. You ignore it in this case and come up with a mathematical justification for it. And the mathematical justification here is that if you think of this as a maximum likelihood estimate, then that term, this second term doesn't matter. And the derivative simply becomes gamma over y. And this is so easy, right? Once you know that the derivative for any cell, the contribution of any cell is simply the gamma of that cell divided by the probability within that cell, then all you have to do to compute this, the derivative of the divergence with respect to the network output at any time, is first, you set the derivative terms for all the symbols that don't occur in this column to 0. For the rest of them, you just count the number of times the symbol occurs and then just multiply gamma over. The gammas are going to be different in these two cases. So you're just going to sum the gammas over all of the cells which have the same symbol, and you divide the sum of the gammas by y. So this is the very simple formula for the derivative of the divergence with respect to the output probability assigned to any symbol. So is this clear? Over here? This one? And so easy, right? And so what is the overall training procedure for this model? Given input and the output sequence without alignment. First, I'm going to set up the network, typically a many-layered LSTM. I initialize all the parameters of the network. Then from the initial model, I'm going to run my data through the network and get these probability vectors at each time, from which I create this reduced probability table and construct the graph. Then on this graph, I run the forward algorithm and the backward algorithm to get alpha and beta. From the alpha and beta, I can compute the gamma for each node. And then once I have the gammas, I can compute the derivatives of the divergence with respect to the output of the network at each time. Through this very simple formula, the derivative of the divergence is simply the vector with respect to any yt is the derivative of the divergence with respect to the vector of the derivatives, partial derivatives with respect to the probabilities assigned to each symbol. some of these will become 0 because they don't feature in the symbol sequence. For the rest of them, you just sum the gammas for all the rows in which that symbol occurs and divide the sum of the gamma by the probability assigned to the symbol. And the negation of that is the derivative of the divergence with respect to the probability of the symbol. So you have now got the derivative of the divergence with respect to the output of the network at each time t, which is just this. And then I can back propagate these derivatives through the rest of the network and train my model, right? So did this whole thing make sense? It's really very efficient. There's nothing fancy. Did this algorithm make sense so far? Yes, sir. Can I see some thumbs ups? 15, 20 maybe. Okay, right. So not so hard, right? So here's the story so far. Sequence to sequence models, which will regularly output symbols, can be decoded through greedy decoding. For training, they require the alignment of the output, the target output, which we don't have. So training can be performed by iteratively estimating the alignment and time synchronous training, or it can be performed by optimizing the expected error over all possible alignments. And for this one, the posterior probabilities of the expectation can be computed using the forward-backward algorithm. So far, so good. But then there was one problem I referred to briefly early in the lecture, which we didn't quite address. Consider the problem where the output symbols are characters, like we have a decode read, right? Is this expanded sequence read or read? Both of them are valid words, right? We don't know if these 4 E's correspond to 1 E or 2 E's. We saw this in the last class. So how do we deal with this? Here's how we deal with this. So this is the issue. You can't distinguish between an extended symbol and repetitions of a symbol. So how do we deal with this? To deal with this, we introduce an explicit extra symbol which serves to separate discrete versions of the symbol. This extra symbol, typically represented by a blank or a hyphen, is to be viewed as an invisible character. It's there, but it's invisible. So if I have an alignment of this kind, RRR, blank, 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 EE, blank, 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 DDD, when I compress it, these 3 R's are going to become 1 R. These 3 blanks are going to compress to, they're invisible, so you won't see them. These 2 E's are going to compress to 1 E. These blanks compress and become invisible. These D's compress to this 1 D. Similarly, if I had something of this kind, the 2 R's will compress to an R, the blank disappears. This E stays, these blank disappears. Now these 2 E's compress to an E and the D compresses to a D. So this becomes read. And so this one over here, the 2 R's become an R, the blank disappears, but the blank separates these 2, right? So this 1 R becomes a new R. Then these blanks disappear, then I get an E, then nothing, then I get a D, then nothing, and then these 2 D's collapse to a D. Is this making sense? How the blank works over here? Yeah. Okay, so can anybody tell me what this last sequence is going to become? If I compress it. It's R, 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 2 E's, and 3 D's, right? Beautiful. And so here is a poll to make sure that you actually got it. Let's see. Okay, 5 seconds, guys. All right, let's stop this poll right here. Here's what you guys thought. So I'm not sure why anybody thought this would collapse to Billy, right? This is going to be B, single I, single L, Y. So it will not have two L's. This is going to have two B's because the two B's are, here's Chin we'll get to that, right? Are separated by a blank. This is going to be BI, but the two L's will collapse to a single L. The only thing that becomes a Billy is this one, because the blanks are separating the two L's, right? So did this make sense? Why this is the only thing that becomes Billy? Or does anybody have any doubt about this? Last chance to ask, otherwise I'm moving on. Okay. So this is the only correct answer, right? So how do you deal with that? Clearly, now this invisible symbol is going to become part of your vocabulary, which means now the network must also compute the probability for the blank, right? So why do the L's need to be separate? I'm asking you for Billy, B-I-L-L-Y. So the two L's need to be separated. That answer your question, Jake? Right. So now the blank is going to be an extra symbol that you compute probabilities for. And so now if you performed a greedy decode and just pick the most likely symbol at each time, these two B's will collapse to a single B. So this is B, E, fur. The four furs will collapse to an and E. So this becomes B, phi. On the other hand, if I have something like this, the blanks disappear, but they separate things on either side. So this becomes B, phi also, right? But what does this become? Can anybody tell me? Over here. What will this become? Anyone? Double F, right? This blank disappears. You're going to get B. These two E's will collapse. You get an F. You have an invisible symbol separating these two F's. So you're going to get a second F. These two F's will collapse in E. So this is going to be B-I, B-E for E. Again, is this okay for you guys? Yes, no? Okay. So we're good, right? But this is going to change how we train things. Remember, if I had a word sequence like 80 before, I'd have pulled out E, A, pulled out D, pulled out D, pulled out E, right? But if I've composed a graph like this, would I actually get an alignment of 80 with two Ds? Over here. Why not? What would I get? It would be E single dy, right? And so what are we going to do? Here's what we will do. Here's how a blank works. A blank is an invisible symbol, right? So if I have, for example, B phi, I can say B is followed by E is followed by phi is followed by E. But if I introduce a blank, this is what the graph looks like. I can have an initial blank because it's an invisible symbol. B can be directly followed by E, or it can be followed by an invisible symbol followed by E. E can be directly followed by F, or it can be followed by an invisible symbol and then an F. F can be followed by E, or it can be followed by an invisible symbol and then an E. So, and of course, E could potentially be followed by an invisible symbol. So do you see how this introduction of B phi changes the graphical representation of what follows what? If I'm trying to generate B phi over here. This making sense? What about the rest of you guys? Can I see some thumbs ups? Oh, wow, it's hard. Okay, a few more. I have 8 thumbs. Can I get 10 at least? That's 1/20th of the class. It's okay. So observe what happened. The moment I introduced a blank, I got a blank between every two symbols, okay? And you're allowed to skip a blank if the symbols on both sides are different. But if the symbols on both sides are the same, they must be separated by the invisible blank. So Pierre, where have I lost you? Pierre, so did this one make sense? The notion of an invisible symbol, Pierre? Okay. So if I want to generate Bifi, here's what I said. I can have B immediately followed by E, but then B could also be followed by an invisible symbol and followed by E. And both of them are going to give me B, B, E. Does that make sense? Here. So same thing in each case. So is this figure making sense? And with that understanding, E can be followed directly by F, or you could have an invisible symbol in between because you can't see it, right? But if you have something like Eddie, things change. I cannot skip from D to D because if I produce A, D, E, the two Ds will collapse. So anytime I have two symbols which are the same, I must have a blank in between. This invisible symbol separating the two copies of the D. So is this making sense? Why we cannot have a skip when the symbols on either side are the same? Yes, no? Give me some thumbs up, guys. Can I see some 10 thumbs up, thumbs at least? I have 3, 8, 10. Okay. All right. So how does this change my alignment? Earlier, I just composed a graph like this, but that's not going to work for Eddie. This is wrong, right? So here's what I'm going to do. I know that when I'm going to use, instead of using this graph, I'm going to use this graph as my template with, optional blanks on either side of each symbol, and except when the two symbols are the same, in which case the blank in between is not optional. So this graph here is, blank A, blank D. You can go straight from A to D. But to go from D to the next D, I have to go through the blank. Then I can go through D to E or directly from D to E, right? So this is the same graph over here, just drawn vertically. And then I'm going to create this table by pulling out the rows of probabilities corresponding to all of these symbols. So observe that the blank row occurs many times, right? And now the graph that I compose is going to have this kind. I'm always going to have, I'm allowed to stay within the same row. Anytime I have a connection between two symbols over here, I'm going to have a diagonal connection going down. So I can go from the blank to A. I can go from the A to the blank, but I can also go from A directly to D. I can go from D to the blank and the blank to D, but I cannot go directly from, so there's no connection of this kind from one D to the other. But from the second D, I can go from the D to the blank like so, or go directly from D to E as shown by this arrow. So this graph here is basically unrolling this graph across time. Do you see how this graph is composed? Here. The rest of you guys. Okay, give me some thumbs up. Be quick, please. I have only 30 minutes to go. All right, thank you. And so now this is the graph that I'm going to be using. Observe though that earlier we only had an A in the beginning. Now you can have either a blank or an A in the beginning. Earlier you only had an E in the end. You're allowed to end either at this node or at this node. So there are two possible initial nodes and two possible terminal nodes. Other than that, nothing else has changed. And these dark blue arrows show the skips that are permitted. No skip is permitted from this D to this D because they are separate symbols. They must be separated by a blank. And now with that in case, I can actually change my forward algorithm. The forward algorithm is still follows the same logic. I'm going to go down the column and compute the alphas for every node. And for any node, the alpha for the node is the sum of the alphas for the parents of that node times the probability of the node itself. The two major differences are that in the first column, I'm going to have non-zero alphas for two nodes because a path can either begin here or over here, right? So the alpha for this node is going to be y0b. For this one, it's going to be y0a. Okay. And for the rest of them, because no paths can begin from here, the alphas are 0. Then when you're going forward, you're going to be summing over all the parents. For some rows, specifically for the rows corresponding to blanks, there are only two parents because you can either have this horizontal connection or a connection immediately above it. For other rows, or or something, or this D over here, right? The D you cannot directly go from this D to D. So this D always has only two parents. For other rows, like say this E, you can either come from E or from the blank before it or the D before it, right? So no, it won't, right? The alignments are just going to, the blank is an invisible symbol, period. Okay. And so you either sum two alphas or three alphas and then multiply it by the node probability. And this is the algorithm you'd use for the forward computation. It's exactly the same algorithm as before, except that the number of parents for any node is not always 2. For some nodes, for nodes corresponding to blanks, there will be 2 parents. For nodes corresponding to symbols where the previous symbol was also the same, then an intervening blank is required, so there will be 2 parents. For all other nodes, there will be 3 parents. That's it. And the actual equation stays the same. Does this make sense? How the alphas are computed? Yes or no? Okay. And how do you think the beta's computation is going to change? Anyone? How is the beta computation going to change? So, any thoughts? For the last column, what will the beta be? Beta hat be? Beta hat's going to be 0 for these guys. You'd have beta hats for only these two nodes, right? And then when you go backwards, what will happen? We will have a sum of the betas, except some nodes will have 3 children and some will have only 2, right? So GI, why is there no connection between Y4D to what there is? There's an arrow, right? Yeah. Okay. And so that's about it. Some will have 3 children, some will have 2. Specifically, you can actually check anything that corresponds to a blank will have only 2 children. Any node where the next symbol is also the same symbol will have only 2 children. The rest of them will have 3 children, except the one at the bottom. And that's it. Posteriors and derivatives are computed same as before, but using the extended graphic blank. So you're going to have to compute gammas for all of the nodes in this graph, right? So Sam, again, because the blank is a generic symbol, you don't necessarily need to put it over here. But you will see why when we talk about decoding in a minute, okay? The blank can also be thought of as a symbol that says nothing interesting happens here. And so that helps, okay? And so now the overall training procedure, same thing, given input and output sequence without alignment, set up the network, initialize all the parameters, except now we include a blank symbol in the vocabulary. Observe that although the blank is not explicitly listed in the vocabulary, it's implicit. we will now include it, and we're going to compute in the forward pass, we're going to compute probabilities for the blanks as well. Then we compose this graph, and you'd use a forward pass, the forward algorithm, to compute the alphas for all the nodes in the graph. Then you'd use the backward algorithm to compute all the betas for all the nodes in the graph. And then you'd use the alphas and betas to compute the gammas, where the gamma is simply the product of the alpha and beta normalized, so that the gammas sum to 1 over the column. And then you can use the gammas to compute the derivative of the divergence with respect to the network output at each time. And this derivative can then be back propagated to train the rest of the network. So did this whole thing make sense, what we've done so far? Yes or no? Give me some thumbs up quickly, please. I'll wait for 15. 7, 8, 9. Okay, one more. Thank you. So this overall framework that we just saw as connection is called connectionist temporal classification. And it applies to models that output order aligned, but time asynchronous outputs like speech recognition, optical character recognition, and so on. Okay, so we know how to train it. I mentioned that decoding was suboptimal, right? Why is that? The greedy decode simply pulls out the most likely symbol at each time. And earlier we said we had this problem that we cannot identify repetitions. But once you introduce a blank, even that problem has gone away. So why is this still suboptimal? For that, let me give you this example. Let's say I have these 6 possible alignments and for an input during inference, okay? And TTEEED, if I look at the probability of this sequence, that's 0.71, but TT-EED is 0.3, TT-ED is 0.29. Observe that all of them collapse to TED. These are 3 different expansions of red. And they all have probabilities which are less than the probability of the most likely expansion of TED. But then, if you look across all possible expansions of TED, this overall has, every possible expansion of red has a high probability, whereas only one of the TEDs has a high probability. Given this, would you choose TED or red as your decode? Which would you choose? Over here. Red, clearly, right? Because red is giving you if you sum over all possible alignments, red has the higher probability. Is this making sense? And so that's what we want to do, right? A greedy decode would pick up TED, but a decode that considers all possible alignments will select red. Red is more reasonable. Yet remarkably, greedy decoding can be very effective in using blanks. Why? It turns out that the blank symbol ends up being a do-nothing symbol. So here's an example from the original paper by Graves. And he shows that when you just print out the probabilities of the various symbols, you find that in most of the regions, the blank symbol has the highest probability. And only when there's a transition that does the symbol corresponding to that particular segment pop up. So a greedy decode over here would actually give you the correct decode, because in all of these steady state regions, the blank simply dominates and manages to capture the probability. Nonetheless, what we really want to do is to find the most likely order aligned symbol sequence rather than the most likely time synchronous symbol sequence. So we want to find the order aligned symbol sequence, which is the compressed sequence that is most likely given the input. Find the order aligned sequence S0 through Sk minus 1, where the number of symbols k themselves might be unknown, such that this has the highest probability given x. How do you do this? We'd have to first compute this term. And for any symbol sequence, we know how to compute the probability of the symbol sequence. You would have to compose this graph, and the total probability of this graph, which is the alpha at this node, is going to be the probability of this symbol sequence. And so, do you remember this? Quickly, this one. Yes or no, guys? Yeah, okay. And so what we'd want to do is to compute the symbol sequence for which this alpha term at the bottom right is the highest. So for every possible symbol sequence, we compose this graph, compute the alpha here, and pick the symbol sequence for which the alpha is highest. What would be the problem with this? Anyone? What would be the problem with this? I'm going to go over a minute, guys. The problem is that for every symbol sequence, you'd have to compose this graph, run the forward algorithm, and then compute the forward probability here, correct? Is that feasible computationally? It's going to be impossible computationally, right? So how do you deal with it? So first, answer this question. The actual objective of decoding is to identify the compressed sequence that has the highest probability, true or false? True or false, guys? Quick. Okay, second statement. This is the same as finding the compressed sequence with the highest forward probability for the final symbol at the final end. This is also true, right? Both are true. So you want to find the symbol sequence with the highest alpha at the bottom right node. This cannot be done explicitly. So here's what we will do. We will organize all possible symbol sequences as a semi-tree. So let's say I'm explaining this. Give me 2 minutes. I'm explaining this using only 2 symbols in my vocabulary, S1 and S2, but then a blank is also there, right? As part of it. So your initial symbol could be a blank, or it could be an S1 or an S2. Then S1 could be followed directly by S2. But then S1 could also be, if S1 is to be followed by S1, there must be an intervening invisible symbol. But then S1 can also be followed by a blank and S2. So this upper path is showing every possible way of generating S1, S1, and S1, S2. Do you see this? Over here. This is every possible way of generating S1, S1, and S1, S2. Same thing over here, right? S2, S1 can be going directly from S2 to S1 or through an invisible symbol, but S2, S2 must go through the invisible symbol. So this is showing all possible ways of generating sequences of up to 2 symbols. I can expand this out and make this infinitely deep, and it will represent symbol sequences of every possible length. Now, each node over here represents a symbol sequence of a specific length. This node represents just S1. This node just represents S2. This node represents S1, S1. This node represents S1, S2. This one represents S1, S1, S2. Right? So I can now place this tree like so against the vertical axis. This is time. And just as I composed my graph before, I drew it from the top to bottom. Here I'm drawing it from the bottom to top. I can unroll this tree across time and I get this crazy graph. Each row over here represents one symbol sequence. For example, this row represents S2, right? Just S2, which can be either directly S2 or blank S2. This row represents S2, 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 right? So this is just this tree. And so now I can run my forward algorithm. And at any time, if I look at the forward probabilities for all the nodes over here, that's going to give me the forward probabilities over here for every possible symbol sequence of length 4, corresponding to an input of length 4. Okay. And except this one will grow arbitrarily It will keep growing as a tree. And so the way we do it to restrict the computation is to use beam search. Within each column, you're only going to retain a small number of the entries and expand only those. I won't get into this too much because beam search is part of your homework. I'll stop right here and apologize for going over time, and I'll take any questions.